Log on, tune in, find out. Another good idea from Cambridge.
You don't need anything else, no?
No.
Chalks and color.
That's fine. Okay, so this is first lecture of hopefully 5. Depends how many of you bear with me until the end. So I'm sorry for the rather vague abstract for these talks, because I couldn't decide for a long time what I actually want to put in these talks. So eventually I will restrict to stability conditions, so mainly talk about stability conditions, but while doing so try to teach you a few standard techniques on derived categories. So this will not be a survey of everything that's known on stability conditions. Neither will I give a very technical introduction, but somehow try to give a mixture of the two. I presume that you're not afraid of derived categories and that you've seen once before what a triangulated category is, although somehow I try to motivate things by sticking to abelian categories whenever this makes sense. So today's talk will be on torsion theories and T structures. So from the title you can see already that this is really not a lecture series for specialists. So if you work with stability conditions on a daily basis, then this is not for you. Okay, so before I talk about these things, I'll give a long introduction motivating things that come up later by recalling things on mu stability of sheaves and curves. So this is part 1, mu stability on curves and maybe a bit on surfaces. So I'll fix a curve C, so that's a smooth projective curve over a field, and for simplicity I assume this field to be algebraically closed. And recall that we say, so if I have this curve, then I'll be interested in the abelian category of coherent sheaves on C. So this is an abelian category. It is actually a k-linear category, but I won't talk about, although very interesting, but I won't talk about the k-linear structure of this abelian category, at least not today and tomorrow. So recall that a coherent sheaf on a curve is mu stable or mu semi-stable if two things hold. First of all, I want this sheaf to be torsion free, which of course on a smooth curve just means it's a vector bundle. So and I want that every proper subsheaf, so which again is a vector bundle, satisfies the slope condition. So the convention is, if I say semi-stable, I want the weak inequality, and if I say stable, I want the strong inequality. Okay. So here mu is of course the slope. So mu of a sheaf is its degree divided by its rank, and you see, assuming that the sheaf is torsion free, ensures that I divide by something non-zero. Okay. Okay, let me rewrite this by using what we later call a stability function as z of e minus the degree of e plus I times the rank. Okay, and so if E is not the zero sheaf, then this can be written, so this is a complex number, so it will be a positive real scalar times the exponential of I times pi of phi e, and this phi e here is called the phase of E. Okay, and the phase, in fact, is I can fix it to be a number between 0 and 1. In other words, this function z here takes values, at least when the sheaf is not 0, in the upper half plane, and we're at the real negative numbers. So, okay, so here's a picture. This is the real upper half plane. We're at the negative real numbers. And so, for instance, for a sheaf that is torsion-free, or at least has a torsion-free, non-trivial torsion-free part, you see that the rank will be positive, and hence its imaginary part will be positive, so it will be in the upper half plane. When the sheaf is torsion, so the rank is 0, then its degree will be positive, because any torsion sheaf has a filtration with coefficients, with quotients isomorphic to some skyscraper sheaf, and the skyscraper sheaf of a point on a curve is always degree 1. And because of this -1 here, you get a real negative number. Okay, so the torsion, so let me put this here. I'll come back to this, but let me finish with the z here. The z has another interesting property, namely that's linear. So if I view this as a function from now allowing also 0 to c, then it factors over the Grothendieck group. So this is the Grothendieck group. So by definition, I take all the isomorphism classes of sheaves to generate a 3 billion group, and then I divide out by short exact sequences. And for a curve, I can easily describe this explicitly, namely as z, which is given by the rank, plus the Picard group of C. So this is the Grothendieck group, and this map Z is linear, so it factors over the Grothendieck group, and the linear map from the Grothendieck group, which is an abelian group, to C. So this is a linear map. Okay, so this is the function Z. And so remarks, clearly E is torsion if and only if Z of E is a real negative number. So all the torsion sheaves will be here. Okay. And the second remark is, if I take now a torsion-free sheaf, then E, so this is the first condition in the definition of mu stability. I want a torsion-free sheaf. So if I now take a torsion-free sheaf, then it is mu semi-stable if and only if for all subsheaves, proper subsheaves, the phase of f is strictly smaller for stability and strictly smaller or equal to the phase of E. So let me again draw a picture. So this is my upper half plane. So now E is torsion free, so its value under this map Z will be in the upper half plane, maybe here, Z of E. If I divide by its rank, then this will be somewhere here, ZE divided by its rank. And you see, if I divide this number by the rank, then its imaginary part is 1. So I will have here 1. And the value I have on the real axis is minus the slope of E, and the phase up to this factor of pi is the angle here. Okay, and now you see that the inequality for the slope in the definition of mu stability translate directly into this inequality for the faces on the other side. Okay. Right. So for arbitrary, we can actually rephrase this. So check for E arbitrary could have torsion, can be torsion free, arbitrary. E is, no, I'm sorry, one step ahead. I take this condition on the face of sub-objects, I call this star, as the new definition for stability. So I used mu stability, not just stability, on curves, and now I say a sheaf on the curve is semi-stable or stable if this condition holds. So E is semi-stable if the condition star holds. So the difference to the definition before is that I allow all sheaves and do not assume the sheaf to be torsion free. So here mu stability had always two parts. First I want to only talk about vector bundles and then this slope condition, and here I put everything in the same condition, which is a condition on the faces of these objects. So this is my definition of stability. Okay, and then check little exercise. Check E is stable if and only if E is mu stable or E is isomorphic to the skyscraper sheaf in one point, at some points X and C. Okay. So the slogan really is, although I somehow will use the slope again and again, you should actually forget everything you ever learned about slopes, and you should speak in terms of faces. Okay, slopes are out, faces are in, so we'll see more often the faces than the slopes. Okay, but here essentially it's equivalent because we're staying in the abelian category. Okay, so what is the next step in the definition in the theory of vector bundles on curves? Well, the next thing is the existence of Hardan-Simon and Jordan-Hölder filtration. Okay, so Hardan-Simon and Jordan-Hölder filtrations. So always use Hn and Kh. And so let me try to do both at the same time. So the existence of Hardan-Simon filtration says that for all, say, non-trivial sheaves on the curve C, there exists a filtration. I start with 0, and then there's a sheaf E1 and so on, such that the quotients AI of this filtration are semi-stable. Are semi-stable of phase phi 1, phi I, and then I have the condition that the phases decrease. Okay, and these AIs here are the semi-stable factors of E. Of E, and the whole thing is the Hardan-Simon filtration of the sheaf E. So for instance, if E is not torsion free, then the first sheaf E1 will always be the torsion part of E, because this is the one with the largest phase, namely only all the torsion sheaves are on the real axis, so they have phase 1. And the phases are between 0 and 1, so 1 is the biggest one. And so E1, if there's any torsion, then E1 will be the torsion of E. So this is the Jordan-Hölder filtration, and you can refine this to make this a Jordan-Hölder filtration, namely by requiring that the factors here are stable of phase phi I, but then you don't have the strict inequalities, you have weak inequalities only. And this is the Jordan-Hölder filtration of E. And the difference between the two, one difference is that the Hardanau-Simon filtration, so recall, the Hardanau-Simon filtration is unique. The Jordan-Hölder filtration is not, in general, not. But the set of stable factors, so for the Jordan-Hölder filtration, these occurring factors are called the stable factors. They are not unique, but they are unique up to permutation, so the set of stable factors is unique. Set of stable factors. Okay. So maybe drawing a picture is always helpful. So if I have my upper half plane, it's more convenient once, this Z here is fixed. If this is fixed, then just to write just E and not Z of E. So if I have any E here, so if it's a torsion sheaf, then it would be on the real axis. If it's not, if it has some, if it has positive rank, then it will be somewhere here. And the stable factors, A1, for instance, will be, if there is any torsion, will be on the real axis. Then there will be maybe an A2 here. And the sum of these stable factors will will add up to E, so there's will be an A3 maybe here. Okay, so this would be for the Hardanau-Simon filtration, and for the Jordan-Hölder filtration, you might have several objects of the same phase, like A1, A2, A3, then A4, A5, and then of course you have to add some others so that the sum again is E. Okay, so what goes into these statements about the Jordan-Hölder and Hardanau-Simon filtration? So the input number of general principles you probably all have seen, namely one is maybe phrased in terms of mu stability. So if E and F are stable, semi-stable, phase of E bigger than the phase of F, then there are no homomorphisms from E to F. If E and F are stable, and the phase of E being bigger or equal to the phase of phi of F, then either E is isomorphic to F, or again there are no homomorphisms from E to F. And then, since we are over an algebraically closed field, if E is stable, then its endomorphism ring is actually K. And here's an exercise. So I was told there are also exercise sessions or tutorials in the afternoon. So if you feel like you're doing some exercises, I put a few in the lectures, and you're free to think about those. That's a bit trickier, but very useful. So if I have an E, a semi-stable sheaf, Okay, so now I can look at the Jordan-Hölder filtration, and I pick one stable factor. So suppose A1 is a stable factor. Not all the stable factors will be subsheaves of E, so I pick one. There will be always one, but maybe more that does. So suppose A1 can be mapped into E. Then there exists a short exact sequence A to E to B such that A and B are again semi-stable. All the stable factors of A are isomorphic to the given one A1 of E. All stable factors of A are actually isomorphic to A1, and there are no homomorphisms from the first one to the second one. So this is something very common for Harder-Neusselmann filtrations. And this is like the first remark here. If the face of E is bigger than the face of F, then there are no homomorphisms. If you want to do this for the Jordan-Hölder filtration, then it's not true, because for instance, the first stable factor can come up as a stable factor in the quotient again. But you can always arrange things that the first thing has only stable factors of a given type, and that there are no homomorphisms from A to B. Okay, so I'll leave this as an exercise. Okay, so this is these are the things I want to record from stability for curves.
I think this is reverse the inequality, right?
No, it's not.
For the
No, that's because of the minus here. I always get confused, but that's so there are no morphisms. Maybe I should tell you, there are no morphisms like this. Okay, let's do this. If mu f is smaller than mu of E, then minus mu of E is smaller than minus mu of F. Right? So the minus mu of E is more to the left, and that means F will be somewhere between here, and the face of F will be strictly smaller than the face of E.
okay, so the phase is from -1 to 0.
No, the phase are from 0 to 1. Okay. Any more questions? Okay, so I'll use this now this situation to introduce some more notation that will be used later again and again. Namely, I'll talk about slices. So for any phi in 0 and 1, I will look at P of phi, which is the collection of all semi-stable sheaves of phase phi. And so it's a collection of objects, but I can actually view this as a full subcategory of the abelian category of all coherent sheaves on C, and these are abelian subcategories. So, for instance, for phi equals 0, for phi equals 1, these are just the torsion sheaves. All the torsion sheaves are on the negative real axis, and then I have P of 1/2. They all lie on the imaginary. Okay, and for instance, this P of 1 here is a Tanaka category, but all the others are just the abelian subcategories, so they're not preserved by the tensor product. One more observation is that, so this is an abelian category, but it's not of finite length, but these sheaves are. These categories are. Here phi are categories of finite length. Which means that any decreasing or ascending or descending chain of subobjects will eventually stabilize, i.e. descending and ascending and ascending chains of subobjects stabilize. And this is essentially the existence of the Jordan-Hölder filtration. If you have a semi-stable sheaf, so an object in one of these categories, you cannot have an infinite, for instance, descending sequence of subobjects, all semi-stable of the same slope or phase. So.
Okay, what's the group?
Question?
What's the group? You said it was Tanaki and I tried
I said this was just a side remark. Forget it. I mean, these categories, they're all.
Just out of curiosity, what's the group?
That's difficult. That's the fundamental group of the curve. It's a Tanaka category because you can take the tensor products, but these are the vector bundles of slope 0, semi-stable vector bundles of slope 0. But describing the group that corresponds to it is that's difficult. Okay. So, moreover, the minimal objects in these categories, so these are categories of finite lengths. And I can look at those objects that do not have any sub-objects any longer, and these are the stable ones. So the minimal, note, the minimal objects are the stable sheaves. So, for instance, for phi equals 1, these are just the skyscraper sheaves again. Okay. So, I need some more notations. So, for instance, for any interval in here, I will look at this subcategory. This is the subcategory of all objects whose semi-stable factors have a phase in this interval, such that all semi-stable factors the phase of AI is in this interval. So these are not abelian categories, subcategories in general. They are only full additive subcategories. Think about it. So if you take the kernel between two semi-stable sheaves of different slope or different phase, it might be something of a slope that is not between the two. So, for instance, if I also use notations like this, if I have here phi, then I will have this one will be denoted by this. So this is actually, we want the subcategory of all sheaves with faces in this. I could also look at the closed interval on the left hand side, or I can look at, I'll give myself another face P of phi prime. I could look at this one, so this would be a subcategory like this. So I can either slice my category in these different rays, in these P of phi's here. So here's P of 1, P of, I'm sorry, this is P of 1 over 2. P of 1, or I can break it in bigger pieces, for instance, P of objects with phase bigger than phi and those smaller than phi, or between in objects with, whose phases are between two given phases. Okay. So in particular, let me do the following. So if I give myself now a phase between 0 and 1, then I define T of phi to be this part here. So this is now little phi, so this will be T of phi. And f of phi to be everything that has phase smaller than or equal to phi. So this is P of 0 phi. Okay. So instead of looking at the Harder-Nach-Simon filtration of an object, I can look at the two parts, one in T and one in F. So then for all sheaves, or let's say not 0, there exists a short exact sequence, E prime going to E double prime. The first one will contain all the semi-stable factors of E of phase bigger than little phi, so this will be in T phi, and this one will be in F phi. And moreover, there are no morphisms from objects in T to objects in F. And T phi, F phi will be 0. Okay. So for instance, if we choose phi to be 1, then this will be the torsion part. So I just split off the torsion of any sheaf, and then this one will be the torsion-free part. But I can choose any other phi that will be will give me a different splitting of the category. Right. So the next thing I want to do is to actually start this first talk by giving the abstract notion of a torsion theory, and this is some of the first example of a torsion theory. Before I do this, let me just make a quick remark on the case of surfaces, and I'll get back to this on Wednesday. So in principle, you could try to do the same thing on a smooth projective surface. So try the same thing. The first thing you have to do is to define the slope, as it's done already. So, and for this you have to pick a divisor, an ample divisor on the surface. And then I can define the degree of any sheaf as the intersection between its first Chern class and the sample divisor. So this will again be a number, and I can define its slope. So the degree will depend on this class H, and this is why I mention it here. It depends on an extra choice, namely on this H. And then, at least if it's not a torsion sheaf, I can divide by its rank. Okay, and in principle, I could write down the same function, this z, depending now on the choice of the ample divisor, and certain things go through. For instance, this splitting of the category and torsion things and non-torsion-free torsion-free sheaves, but other things do not go through. For instance, if I take a sheaf that's concentrated in dimension 0, for instance, a point sheaf, it will go to 0 under this map. It has neither a rank nor a degree. Well, it has, but both are 0. And the existence of Jordan-Hölder filtration on for sheaves concentrated in dimension 1, so on curves, is not given. And this naive approach to do the same thing in higher dimensions by choosing an empty divisor breaks down. I don't get the same nice picture as before. So in order to make this work, you have to divide the abelian category of covariant sheaves on S by sheaves that are concentrated in points, so by zero-dimensional sheaves. And then there's a theory very similar to the case of curves, but the space of stability conditions, which we'll analyze for curves, is more complicated in this case. So this is work of Meinhardt and Pouch. Of course, the natural reflex, if you have ever thought about stable sheaves on surfaces, is not to take slope stabilities or not to work with a slope, but with Giesecke stability, so taking into account the whole Hilbert polynomial. But if you try to formalize this in the same way, then you will see that the stability function you can write down, so something that takes care of the whole Hilbert polynomial, will not take values in the complex plane, but in something more complicated, because the Hilbert polynomial will have 3 coefficients and not just 2, like in the case of curves.
Can I just check your definition here? You said when you take phi equals 1, the t gives you the torsion.
No, the t is the torsion, yes.
And the f gives you the torsion free.
Right.
Wouldn't you need less than 1?
Here, no, so I said a sheaf is torsion if and only if its phase is 1. So these will be the torsion sheaves, and these are the torsion-free sheaves.
So you said well, less than equals 1.
I'm sorry. That's yes, that's true. So okay, I'm sorry. They can equally well build a theory. I mean, if I take phi equals 1, this one would be actually empty here. So what I can also write down, this is another thing. I could take the closed interval on the left and the open interval on the right hand side. This would also give a splitting would satisfy the same conditions as this one, and actually you're right, for phi equals 1 would make more sense. But my choice for the t to have an open interval on the left is motivated by something I'll say on Wednesday. So okay.
Can I ask about this degree in the surface case?
Yes.
Is it the same as the degree of the restriction to the device?
Yes. Okay, so torsion theories and abelian categories. So I tried to get you used slowly to the idea of a stability condition. So I won't define what a stability condition is today, tomorrow, but I want to talk about torsion theories and T structures. So, and I start with torsion theories. And so this is this goes back to I was told to Dixon. I can remember this date, so this is 66. But apparently, some of the idea was appeared before in work of Gabriel. Then there is an important memoirs of the AMS, Happel, Reiten, Smaller. This is 96. And then there's a new one, well, more recent one by Beligianis and Reiten in 2007. I think it's also a memo of the AMS. And so A will always be, well, usually be in the abelian category. And a torsion theory or a torsion pair, so this is the same thing as a torsion pair, consists of two full additive subcategories of A such that satisfying essentially these two properties here. These two properties, namely, there are no morphisms from T to F. So whenever I write this, I mean for any objects in T and any object in F, there won't be any non-trivial morphisms from this object from the first to the second. Okay. This. Okay. And for all objects in the abelian category, there will be a short exact sequence where the first one is in T and the second one is in F. Okay, so maybe a couple of remarks. First one, this sequence, I should put it on here. Let me see. So the first remark is this sequence here is unique. For any E. This essentially follows from the first condition that there are no morphisms. So just write another short exact sequence of this type, and then you will find that the other element in T sitting in E, the quotient in F, will map to here, but this map must be 0 because of the first condition, and you get an isomorphism to the element in the first one. The second is you can actually use this unicity of the short exact sequence to define right adjoint functor to the inclusion of T in A. That maps, so this would be then a functor from A to T that maps E to this E prime. So you should really think of, that's where the name comes from the torsion theory. You should think of the torsion of a modulo of a sheaf, and you can always associate the torsion of a sheaf to a sheaf, and that would give you a functor from the abelian category, for instance, of coherent sheaves, to the subcategory of torsion sheaves, and this is turns out to be right adjoint to the inclusion. And you can actually forget about the F by observing that the F is the right orthogonal to T. So this is another piece of notation. So this is the subcategory. So this is the definition. The subcategory of all objects in A that has no morphisms from objects in T. So this is again a direct consequence of these two conditions, and so in a sense, the torsion theory is actually given by one category, by this category T, which is an additive category, and the F then is constructed as the right orthogonal complement. And there's an interesting proposition in this memoir of Peligianis and Reiten that characterizes the T's. So T in A defines a torsion pair if and only if what is it? Two conditions. The right adjoint. So there exists a right adjoint to the inclusion, and T is closed under right exact sequences. Right exact sequences. Let me not go into this, but there's a natural question to characterize actually the full additive subcategories that occur as the torsion part of a torsion theory. Closed under x, for instance, closed under short exact sequence means if the outer terms are in this category, then also the one in the middle. And closed under right exact sequences means you allow the first morphism not to be injective. So slightly stronger than being closed under short exact sequences. Okay, so so the why are these things interesting, as we will see in detail, is that torsion theories, so the observations or the factors, torsion pairs yield new abelian categories. So the standard way to do this is to work in derived categories or in triangulated categories with T structures. There is a way, I just mentioned it, if you're interested you can look it up. There's a way to deal with these what are called tilts of abelian categories without derived categories. And this is in a paper by Noe, which is on the archive a couple of years ago. And he does this without derived categories. And in a very explicit way. So if you want to work with these tilts, which I'll explain in like 5 minutes, then you can look it up there. So I'll come to this, but before I do this, I want to recall the notion of a T structure. And I want to do this in analogy to the theory of a torsion theory or torsion pair for an abelian category. So my standard notation for a triangulated category will be D. So this is always a right, and you should think of it as, for instance, the bounded derived category of an abelian category, maybe of this abelian category, A. Bounded derived category A. So I don't go into the definition of a triangulated category. The only thing I want to recall is there are two structures, namely there exists the shift functor, which is an autoequivalence, which is written like this, at least for an algebraic geometer. A topologist would write a sigma. And there's the notion of exact triangles replacing short exact sequences in A. So the triangulated category is an additive category, but it's not abelian. And triangles are written in the form E, F, G, and then there's always this boundary map to E shifted by 1, or to stress the fact that it's a triangle. It's written as a triangle, where this morphism here is actually of degree 1, because it's not really morphism from G to E, but from G to the image of E under this autoequivalence given by the shift. Okay, so in the case of the bounded derived category, the shift functor is really taking a complex and shifting it to the left by 1, and the standard triangle in the bounded derived category is really the cone of a map of complexes. Okay, so that's all I want to say about triangulated categories. Maybe, well, no, maybe not quite. Maybe I should. So, of course, these axioms TR1 to TR4, and just to remind you of two consequences. One of these axioms, I always forget which one, says that I can rotate a triangle and it becomes still a triangle by changing somewhere a sign. So rotation of a triangle again again a triangle, and applying the Hom functor in the second and the first variable gives long exact sequences. Long exact sequences. And my notation for use both xi, ab is by definition the space of morphisms from A to B shifted by I, and which I also write as Hom I AB. So this is just a piece of notation. Okay, so somehow I have to assume that you're familiar with the triangulated category, that at least you have seen the boundary derived category of an abelian category. Okay, so now I just try to imitate the definition of a torsion theory over there, and so definition, a T structure on D consists of a full additive subcategory such that well, the first one, I just turn this into a definition, namely I just define F to be the right orthogonal complement of T, just take the same definition. Then the second condition is the existence of a short exact sequence for each object E, and so there are no short exact sequence in the triangulated category, but those are replaced by exact triangles. So just take this definition and say for all objects in D there exists an exact triangle of the form E prime E E double prime. This is in T and this is in F. Okay, short exact sequences get replaced by exact triangles, and now taking into account this other structure, namely the existence of the shift, adds another condition which wasn't present in the case of abelian categories. I want the category T not to be preserved by the shift, but to give a subcategory of T. So this is not an equivalence, not an equality of the two subcategories. It's in general it's a strict. Well, it's always a strict. No, it's not always, but it's in general it's a strict inclusion. Okay. So the shift just wasn't there in the abelian case, and now it's there, and then incorporated as a condition there. So the standard notation is more like. So I first wanted to present it in this using the notation T and F as in the abelian case, but the standard notation is more like T smaller or equal to 0 is the T, and T bigger than 0, or which is the same, bigger than or equal to 1 is the subcategory F. So this is the standard notation, and this exact triangle here then is written rather in this form, and for instance the truncation functor here, this tau is right adjoint to the inclusion. So it's very similar to the abelian case, with the exception of this shift. Okay.
Do you have to require the existence of the right adjoint to the inclusion, or is that automatic?
No, that's automatic. This is again as before, by this condition here, this one will be unique, this exact triangle. It's again, as in the abelian case, a consequence of me. So there's another piece of notation, namely, hope I remember this correctly. So this one is D smaller than or equal to 0 shifted by minus I. To get this right, you always have to think. Well, I'll give you the standard example of of a T structure, and then some of the where this is really the shift of complexes, and then you can remember these the sign there. So the heart of a T structure is this thing. So here is plus or minus 1. It's plus 1. Okay. So this is the heart of a T structure, and the fact is that so there was no A before. Even if you started with a bounded derived category, often a abelian category, you consider an arbitrary T structure, all of a sudden you get a new abelian category that might not have anything to do with the one you started with. If you start with an arbitrary triangulated category, then there's no possible confusion because there was no abelian category to start with. So here I get a T structure. If I have a T structure, I take the heart, and the heart is always is an abelian category. And the useful as one useful functor for each I, taking the this is like taking the cohomology, and this maps the sheaf. An object E to this object. I apply the truncation functors given by the bounded T structure to the left and to the right, and I get an object in the abelian category. So this would be the case for I equals 0, and then of course I can do this for any I and get it for arbitrary.
Is it possible that half is only 0?
No. Well, it depends on the derived category. I mean, on the triangulated category. So if the triangulated category was essentially nothing, then also the A.
No, if I take tau to be everything.
Tau to be.
Then what he says will happen. Tau can be 0 or everything. You are not ruled that out.
Right. Okay. Yes. Okay. So maybe the standard example is, of course, D equals the bounded derived category, for instance, and I take this one to be the subcategory of objects with cohomology concentrated in negative degree, and then this one would be the one concentrated in positive degree. This is the standard T structure, and its heart is the original A. So on a bounded derived category, you always have a T structure. In fact, this one has the additional property of being a bounded T structure. So and the bounded T structure, so T structure is bounded if for every object there exists an n such that E so usually the n will be very big, and every object is bounded from the left and from the right in this sense of being contained in the subcategory. So on the bounded derived category, the standard T structure is bounded. If you, instead of taking the bounded derived category, the unbounded derived category, then the standard T structure will not be bounded. Okay, so there are certainly T structures that are not bounded, And in fact, the admitting a bounded T structure is a condition on the category. So there's the, maybe I'll conclude with this. There's the following folklore result, which was recently written up by Lee and Chen. So this is the Journal of Algebra 2007, proving that if a triangulated category has a bounded T structure, then it is Karoubian. If D admits a bounded T structure, so bounded is important here, bounded T structure, then it is so what is called Karoubian, or Karoubian, or that is other people. Some people say idempotent split. So this is a real condition. Let me just put here the definition. So Karoubian means, or idempotent split means that whenever I have a morphism, an endomorphism of an object which is an idempotent, so E square equals E, then there's actually the E can be split into a direct sum, E1 plus E2, and the E is obtained by taking the natural, sorry, this is the projection to E1, and I also have the inclusion. So then E can be written as the composition of the natural inclusion and the projection. And they're actually very nice categories that are not idempotent split and hence cannot admit a bounded T structure. So the admitting a bounded T structure is really a condition on the triangulated category. Okay. That's a natural question. So, for instance, if you start with bounded derived category of an abelian category, you put a bounded T structure on it, and you end up with another abelian category that might have nothing to do with the original one. And now you can take the bounded derived category of this one, and you wonder whether you get the same triangulated category. This is the question, right? And this is a question which is in general difficult to answer. We'll see examples where the T structure comes from a torsion theory, and then there's a condition on the torsion theory that ensures that the two derived categories are equivalent. Nothing I'm aware of. I'll talk about this then tomorrow, and we'll also define what actually a stability condition is. Okay.
Questions?